You've had a little bit of an introduction to relative motion now, if you read the book and watched the video that I had posted earlier than this one. So now let's look at an example. While driving back from Spokane after one of my daughter's soccer games, we were going against a very strong wind out of the west. Our 1988 Plymouth Voyager was straining to drive even 65 miles an hour. I noticed a single-engine plane with pontoons, so it can land on water, flying just a few hundred feet above the ground and parallel to the freeway. We were on a stretch where the freeway is due west between Ritzville and Moses Lake. I soon realized that we were catching up to the airplane. Eventually, we passed the airplane, and I estimated we were going only about 3 miles per hour faster than the plane. How fast was the plane going with respect to the ground? You can probably do this problem in your head, and you have a little bit of an intuitive feeling for it, but let's set it up with the relative velocity equations so that we'll be able to duplicate this process on more complicated problems. In that relative velocity introductory material, you probably got the impression that there are two reference frames from which you observe things. And reference frame A, we're going to call the one that's with respect to the Earth. Reference B, in this case, is going to be a viewpoint or a reference frame with respect to something that's moving at constant velocity that usually we know the speed of. In part B of this, we won't. Most of the time we know that. And in this case, it's going to be the viewpoint with respect to the car. Then there's an object. In this case, it's the airplane, for part A at least. And we're interested in that. I'm going to call P the object of interest because it's an airplane. Now, this is a one-dimensional problem, so I can have all of these things, arrows pointing in the same direction, and we're going to be looking down at this. One of the things will be the velocity of the plane with respect to A, with respect to the Earth. Another thing will be the velocity of the car, point B, with respect to the Earth. So we'll have the velocity of B with respect to the Earth, and that's supposed to be a slash there. And a third thing that we'll have here is the velocity of the plane with respect to the car. Okay, now the car happened to be catching up to this thing, so the velocity of the plane with respect to the car is actually pointing back this way. So velocity of the plane with respect to the car, which is B. So that's what we have. Now, the velocity of the plane with respect to the Earth, this one should have been VB/A. I'm going to use E for the Earth. There we go. That'll make this a whole lot easier. Velocity of the plane with respect to the Earth. Yeah, let's use E for Earth every time. The velocity of the plane with respect to the Earth in one dimension will equal the velocity of the car with respect to the Earth plus the velocity of the plane with respect to the car, V. And I should have used C for car. That would have made a whole lot more sense. But then it wouldn't be my brain if it made a whole lot of sense. We can just say we know the velocity. We don't know the velocity of the plane with respect to the ground. That's what we're after for part A. We know the velocity of the car with respect to the Earth. That's 65 miles per hour. And I estimated that the velocity of the plane with respect to the car was about 3 miles per hour. Okay, but we were catching up to it. And so this would be minus 3 miles per hour with respect to the car. And so what we get is that the velocity of the plane with respect to the Earth is equal to 62 miles per hour. That's the way that we add these things. Now there's a second part of this problem. The second part is, what was the wind speed on this day? I'm going to set up a different coordinate system, or at least one different one. This is for part B here. E is going to be, again, that'll be the viewpoint with respect to the Earth. W is going to be, in this case, the viewpoint with respect to the wind. And P is still our object of interest. And so we will have the velocity of the plane with respect to the Earth, which we happen to know. We'll have the velocity of the wind with respect to the Earth, which we don't know. And finally, we'll have the velocity of the plane with respect to the wind. The velocity of the plane with respect to the Earth, this is the way these things get set up, will equal the velocity of the wind with respect to the Earth plus the velocity of the plane with respect to the wind. But we want the velocity of the wind with respect to the Earth here. Now, we happen to know the velocity of the plane with respect to the Earth is 62 miles per hour. We happen to know that the velocity of the plane with respect to the wind is 110 miles per hour. And it's the velocity of the wind with respect to the Earth that we don't know. Well, velocity of the plane with respect to the Earth minus the velocity of the plane with respect to the wind is equal to the velocity of the wind with respect to the Earth. So it's going to be 62 miles per hour minus 110 miles per hour. And we get about minus 48 miles per hour, and that's the velocity of the wind with respect to the Earth. Now, in the way I've done this problem, I was assuming that west was the positive direction, so when I get a negative velocity for this velocity of the wind with respect to the Earth, it's blowing out of the west or toward the east. So that was the wind speed on that day. It was kind of an amazing day. When we got back to Moses Lake, pretty good dust storm going on. You could watch parts of Quincy and George blowing by.